So what I want to talk about this lecture is okay, so remember, the quest for this first part has always been to have simple ascending auctions. And it was always the case that a sanity check would be, well, there better at least be a polynomial time dominant strategy implementation. And of course, for welfare maximization, that means VCG. So we always paused for like 2 seconds to say, okay, well, VCG is in polynomial time at least, right? Now, it turns out, once we get to the generality of gross substitutes, it is actually quite a bit of work to prove that you can implement VCG in polynomial time. And that's the goal of this lecture. And what's interesting is we're actually going to use the stuff we talked about last lecture, the fact, well, Walrasian equilibria are guaranteed to exist. We're going to use that directly in proving that we can implement this in polynomial time. Okay? So hopefully this will give you sort of some indication of all the intricate connections between properties of gross substitutes valuations. Because again, these two seem like to have very little to do with each other. Right? Walrasian equilibria was just an existence question, seems to have nothing to do with computation, and then the payments weren't the same as the VCG payments. And so now here we're switching to computation, we're switching to VCG, and yet somehow the same condition is sort of the right one. Okay? All right, so poly-time implementation of VCG. Okay. Right, so a couple comments. So we're going to do this using linear programming, okay, both to sort of reason about how this might work, and then the actual algorithm will use linear programming as well. It will be not practical at all. Okay, so the point is just to show today, in principle, you can do welfare maximization and therefore the VCG mechanism in polynomial time with gross substitutes. I mean, keep in mind, we're going to be using pretty heavy machinery, but I mean, keep in mind this is somehow a pretty big generalization of bipartite matching, which is already not the most trivial problem to put in polynomial time. Okay, we're really going significantly beyond that. Speaking of bipartite matching, I want to basically develop all the relevant linear programming in the context just of scenario number 3, just in the context of unit demand bidders, where we can think about welfare maximization as bipartite matching. The reason I'm going to do that is because the general proofs are exactly the same proofs. But it's going to be, I think, quite a bit easier to just understand what's going on if we keep it concrete for bipartite matching. Okay, so we're going to go retro for a little bit, back to scenario 3. So warm up. Unit demand. So let's think, so if you knew some linear programming and you never knew that there were combinatorial algorithms for bipartite matching, let's give an argument about why the VCG mechanism can be implemented in polynomial time via linear programming. Along the way, we'll get a very satisfying interpretation of Walrasian equilibria in terms of optimal dual solutions, which is actually a good way to think about them. Okay? All right, so let's start with an integer programming formulation of welfare maximization in this setting. And again, welfare maximization is just bipartite matching, where you have the bidders on one side. Again, this is for the unit demand case. Items on the other side, and it's a complete graph, and the weight of an edge is Vij, bidder i's value for good j. Okay, so welfare maximization is exactly the same as max weight bipartite matching in this graph. So let's encode this as an integer program. So we're going to have one decision variable, xij, either 0 or 1, for each bidder I and item j. 1 just denotes that j gets assigned to I. 0 means j is not assigned to I. Okay? So we should talk about what we want, what's our objective, and then what are the constraints. So we want to max welfare. Right? So the welfare is just, well, let's look at each bidder I in turn. Let's look at the goods that I might have gotten. And whenever xij equals 1, meaning in fact item j goes to bidder I, that contributes Vij to the welfare. Okay? So this is just the welfare objective. Now for this to make sense, two constraints have to be true. So first of all, an item, of course, can only go to one person. So we have at most one. And this is summing over all the bidders to whom it might be assigned. And then second of all, in a unit demand case, we want to focus on just bidders getting a single item, because remember, they don't want more than one. So we have another set of constraints for all bidders I. And again, this is at most one. And now it's a sum over all the items, j, that the bidder might get. Okay. So the assertion, which I can elaborate on if you want, but I won't if you don't ask, is that this integer program exactly encodes the max weight bipartite matching. Okay, feasible 0-1 solutions to this exactly correspond to bipartite matchings, and the objective function exactly corresponds to welfare. Okay. So any questions about that? All right, now, so lots of integer programs are hard to solve. This one is not. Many of you have seen bipartite matching algorithms, which, whether they know it or not, are producing optimal solutions to this integer program. That said, I still want to think about the linear programming relaxation. Okay, often linear programming relaxations are for problems that are NP hard, which this one is not. But still, I want to think about duals. That's useful interpreting Walrasian equilibria. Okay, duals of what? Duals of this program's linear relaxation. So what's a linear relaxation? It just means that we remove the only thing which is not linear, namely this. Okay, this is a binary constraint, and we replace this with a linear constraint. Okay. So LP relaxation, you take each constraint of this form, and you replace it with the constraint xij is non-negative. Your first thought might be to also have a constraint that xij is at most 1. Notice that would be redundant with these constraints. So we're just going to have xij non-negative. Okay? Now, this is a linear program. Okay? And linear programs can be solved in polynomial time. Okay, that's not an obvious fact, and I'm certainly not going to prove it in this class, but it's a true fact which you should know. Okay, so linear programs can be solved both in theory and in practice. Okay? Okay, good. Now, let's think about the dual linear program. So let me actually just do a little review of duals and what they mean and where they come from. So we'll call this the primal linear program, okay, in this context. So the point of a dual, what it's really doing is it's encoding a family of upper bounds on how big the optimal solution to this linear program can possibly be. Okay? So this linear program has some optimal objective function value, 123 or whatever, and I'm going to give you a way to encode proofs that this optimal value is at most something. Okay? So let me be more concrete. So let's do a thought experiment. So imagine, so how would I convince you that the optimal solution to this linear program is at most whatever, has value at most 123? Well, here's an approach I could try to use to convince you that you can't do better than 143. Suppose I dream up some non-negative weights, both for the items and for the bidders. Okay? So it doesn't matter where these come from. So non-negative weights to the bidders. So I'm going to call these the UIs. Eventually we'll be able to interpret them as utilities. And the items, so these are the PJs, which eventually we'll be able to interpret as prices. Okay, so inside, so if we think of this as a bipartite graph, the nodes corresponding to the bidders get these weights UIs, and the nodes corresponding to the items get these weights, the PJs. And suppose I cover the values of all the edges, so that all edges are covered in the sense that if I sum up the weights on the edges endpoints, so think about just a pair, ij, and I compare the sum of the weights of its two endpoints, namely ui and pj, with the weights or the value of that edge, vij, the node endpoint weight should be at least as big as the edge value. Okay, so that's what I mean by these weights covering all of the edge values. Suppose the sum of these weights, all of the ui's and all of the pj's, suppose the sum of all of these is at most 143. I claim then you have to admit that the max value of any matching is at most 143. So why is that true? Well, for any matching, okay, so when you pick an edge ij, of course the contribution to the welfare is vij. But you know what? I'm going to be a nice guy. Okay, I'm not going to give you vij. I'm going to give you ui plus pj. Okay, instead of vij, the edge value, I'm going to give you the sum of the edges, the endpoints weights. Okay, which is at least as large. So I'm doing you a favor. I'm giving you a larger number. Now it's a matching, so each node on each side only participates in one edge. So this node I with weight ui, that's only going to contribute to the sum once. And this node j with weight pj, that's only going to contribute to the sum once. So the best case scenario is you pick up each of these weights from every possible node once. That's the sum of the pj's and the sum of the ui's. Okay? So that's definitely an overestimate on the value of any matching. Agreed? So this is, so notice, like for the matching problem, if you wanted to convince me that the optimal solution is at least some value, like 111, it's clear how you do that. Show me the matching. I'd inspect it, count up the values, I'd be like, yep, that's 111. The best matching is at least as good. So this is how we get bounds on the other side, from above. Okay, we're putting node weights that cover the edge values, and then summing up all of the node weights. Okay? All right, so this is a generic method you could use to upper bound the value of the max weight matching. The dual linear program, by construction, by definition, is just the best, the smallest upper bound you could ever prove this way. Okay? Oh, something I forgot to say. So note, the upper bound argument I just gave, it doesn't just apply to matchings. It also applies to so-called fractional matchings. That is, it applies to any feasible solution of this linear program. For exactly the same reason. Okay, so if you pick an edge at 0.5, again, instead of giving you 0.5 times its weight, I'll be a nice guy. I'll give you 0.5 times the sum of the weights at its endpoints. This says that, counting up over all edges incident on a bit or I, it's going to contribute at most 1 overall. So at best, you'll get the full ui contribution from this bit or I, and at most, you'll get the full pj contribution from a good j. Okay, so even if it's a fractional matching, which is a bigger set, okay, there's only more of them, but these proofs also upper bound the best possible fractional matching. So anything feasible for this linear program is upper bounded by the sum of the weights for any choice of non-negative weights so that all edges are covered. And again, the dual LP is just the best, i.e. smallest upper bound of this form. So formally, the dual LP is, well, so we have this constraint here. ui plus pj is at most vij. Looking ahead, let me suggest rewriting this constraint as ui at least vij minus pj to be suggested. It's the same constraint for all ij. As I said, all these things should be non-negative. And amongst all such upper bound proofs and the corresponding upper bounds that they give, we want the best one possible. So we minimize. Okay. So we've already proved weak duality, which says that the objective function value of every primal feasible solution, that is every fractional matching, is bounded above by any of these. Any feasible solution gives an upper bound. And again, when I hear, so in the primal, when I say objective function value, I mean this. Over here, when I say the dual objective function value, I mean this. Okay. Okay. So this we already proved. Okay, that was the argument about being a nice guy and so on. Okay, so good. So that's weak duality. That's very important. Let me just sort of emphasize, especially if you haven't followed literally everything I've said, just keep in mind if you ever review this later, basically nothing up to here has any math content whatsoever. Okay, there's conceptual content in the sense I think this is a good way to think about stuff, but this is all by construction, by definition up to this point. Okay, there's been nothing non-trivial. Okay, and so actually I'm going to continue that for a second. Really, there's only going to be one non-trivial thing. And again, when I say trivial, I don't mean it should make sense the first time you see it. That's not what I mean. I mean at some point, if it's not crystal clear now, you can definitely get to a point where it's crystal clear. That's what I mean. Okay. So what I want to ask next is, so we have this inequality. You take any primal solution, any fractional matching, you take any covering of the nodes of this form, and you know that the primal objective function value can only be less than the dual objective function value. And now I want to say under what conditions, okay, joint conditions on this pair, the primal dual feasible pair, when would it ever be the case that this inequality holds with equality? Okay, so that's going to give us what's called complementary slackness conditions. So question, when does equality hold for some primal dual pair? Okay. Well, I mean in general, suppose you have a chain of inequalities, right? A is a most B is a most C is a most D. And you want to ask, when is A equal D? Well, they're equal exactly when all of the inequalities in the middle hold with equality. Okay? So weak duality, we argued through why this was an inequality. Right, we said, well, you know, over here, you get the fractional matching. And then, you know, we can have this upper bound where instead of doing Vij, we could instead charge something which is only more, ui plus pj, because that's the first inequality. Instead of using the Vij's, we use the sum of the weights of the endpoints. We used it in two other analogous ways. So first we said, at best, you get the full weight u sub I. You might get less. And we also said, at best, you might get the full weight p sub j from item j. You might get less. Okay, so those are the three inequalities. And so weak duality will hold with equality if and only if those three inequalities are tight, hold with equality. Okay? So that's complementary slackness. Complementary slackness is just saying they're just the conditions that those three inequalities hold with equality. So formally, so answer, if and only if. All right, so we have the first one. To the first potential sloppiness was that the sum of the weights of an edge might exceed the value. So we want that to hold with equality. Okay, one exception. I mean, so if an edge doesn't participate in the matching at all, if xij is 0, then who cares? right? It's as if that edge didn't exist, so we don't care about this. So really what we mean is there should be no overestimate. Or again, it might be more suggestive to write ui equals vij minus pj, looking ahead. Whenever the pair ij is actually put to use, whenever xij is strictly positive. And then we have the analogous ones about just saying, you know, it better be that actually you don't just get up to 1 unit of the ui, you better get the full ui. Okay? Well, unless ui is 0, then who cares? And similarly, as long as pj is not 0, you better use it fully. Okay? So in terms of this graph, the first condition says, you know, consider any fractional matching, right? So that's just sort of a percentage of use on each of these edges. It's saying unless this is 0, it better be the case that the two node endpoints is exactly the value. And then the second one, that's referring to the bidders. So it says just the total fraction on edges that are incident to that node on the left-hand side should be 1, unless its value is 0. And then the third condition is the same thing about nodes on the right-hand side and the incident edges, adding up to 1. Okay? Okay, so that is the answer. Okay, so just, again, this is just nothing but straightforward algebra. The answer to when would you have equality here, if I gave you a given feasible primal solution and feasible dual solution, if and only if these three conditions satisfy. Okay, just because whenever you have a chain of inequalities, you know, to have equality at the endpoints, you need equality everywhere in between. Okay, that's all this is. Now, here is the one statement with significant mathematical content. Strong duality. You know, again, don't be too scared of this if you've never seen it before. We could prove this in maybe 45 minutes at the most. I'm not going to do it here. I'll put some notes on the course webpage if you want to read more. So strong duality says it is always possible for any linear program, in particular for these, to choose a feasible solution to the primal and to the dual so that this holds with equality. Okay? And that is not obvious. So in other words, I talked about these dual solutions as being a method by which you could generate upper bounds on the optimal solution to a matching. But who's to say that there isn't some other class of much better upper bounds that will give you much sort of tighter understanding of what the optimal solution is? So strong duality says, no, don't worry about it. Okay? All you need are these dual arguments. This is sufficient to prove the correct upper bound, okay? To prove an upper bound that's equal to the actual optimal solution value. So strong duality says the optimal primal value equals the optimal dual value. Okay? Questions? All right. So, good. So that's important. And then corollary is important. So now suppose, so the point is going to be that complementary slackness characterizes optimality of linear programs. Okay, and that's going to be very useful for us in a second. So even without strong duality, let me point out the following. Okay, so forget about this for a second. So suppose you didn't know whether strong duality held or not, but suppose I succeeded in coming up with a primal dual pair so that all three of these conditions hold. Okay, so I show you a matching, and I show you these node weights, and it's the case, you just read them off. You just check that all these three conditions are satisfied by that primal dual pair. What do you know? Well, first of all, this is necessary and sufficient to have equality. Okay? So that means that, you know, this primal solution has value 123, and so does the dual solution have 123. Okay? So by checking these, you immediately know that they have an identical objective function value. And then you go over and you look just at weak duality, and you say, oh, wait a minute. Well, if there's no way a primal can be bigger than any dual, and there's no way a dual can be smaller than any primal, and I just found a primal and a dual with exactly the same value, that automatically certifies the optimality of both. Okay? Even if you don't know strong duality is true. Okay? So the point is, if I ever show you something that satisfies complementary slackness, you know the involved primal and the involved dual have to be optimal, just from weak duality. Okay? Because again, no primal can ever be bigger than a dual. So if you have a primal that's equal to a dual, that's as high as it gets. Same thing, no dual can be less than a primal, so if it goes all the way down to a primal, then it can't get any lower. Okay? So one direction, you don't even need strong duality. If complementary slackness holds, then both of the involved primal and dual solutions have to be not just feasible, but they have to both be optimal. Okay, so that's statement one. Now, strong duality says, well, look, in any linear program, there is going to be a pair where the objective function values meet, and therefore, of course, are optimal. Okay? So what that means is, if you don't satisfy the complementary slackness conditions, okay, well then you're not going to have equality. The primal objective won't equal the dual objective. So then they're not both optimal. One might be optimal, but they're not both optimal. Okay? Strong duality says something out there meets with equality. Those are the optimal ones. So if I show a primal and a dual that has a gap, one of them is not optimal. And if you don't meet the complementary slackness, then you have a gap. Okay? So summarizing, we have the following. Let X be primal feasible. Let U comma P, remember in the dual we have both U's and P's. So let UP be dual feasible. So what we now have is that then X and UP are both optimal for their respective linear programs if and only if CS1 through CS3 hold. Okay? That's what we just talked through. And again, this direction only requires weak duality. Okay? Whenever you see all of these three, you get identical objective function values. That certifies both as optimal. But strong duality says, in fact, that's the only way to be optimal. Okay? There's no way that something that doesn't satisfy this will ever satisfy that. Okay? All right, so any questions about that? All right, so I hope that was good review. Now what I want to do is I want to connect all this stuff to the existence of Walrasian equilibria. Okay, so stuff starts getting kind of cool here. So here's the theorem, and this theorem will follow, really quite directly from this complementary slackness condition, quite directly from this corollary. So the way I'm going to state this theorem is going to look a little weird for the bipartite matching special case, but it's going to generalize effortlessly. So that's why I'm going to state it in this particular way. All right, so we've got our linear program. Sorry, we've got our integer program where the feasible solutions are matchings. So call opt LP and opt IP the opt value of the primal LP and the opt value of the original IP. So of course the primal LP, this is only bigger, right? So we're maximizing. Here the feasible solutions are these 0, 1 points only. And here that feasible solution is those same 0, 1 points plus a bunch of fractional stuff, right? So opt LP is only going to be at least as large as opt IP, okay? So here's what the theorem says. There's two parts. So first of all, again, and this statement will look a little weird the way I write it. There exists a Walrasian equilibrium if and only if, in fact, the linear programming relaxation is exact in the sense that both the integer program and its linear relaxation have identical objective function value. Okay, so this is claim one. Now, why is this weird? It's sort of weird to write this because the left-hand side, what do we know about the left-hand side in this bipartite matching context? It's true. We just know this is true, right? Yeah, so I mean, this if and only if makes it sound like there are cases where it's true and cases where it's not. Okay, but again, thinking forward, this will make more sense. Okay, but for unit demand bidders, for bipartite matching, this always holds. So in particular, this is asserting that for any bipartite matching problem, in fact, the linear relaxation is exact. Now that's a well-known fact. Okay, this isn't some novel proof of that. Okay, people have known this forever. Okay, but I mean, you know, certainly the coincidence should be reassuring in this case. Okay, so here's something which has a little more meat in the current context. In this case, meaning when Walrasian equilibria exists, meaning for bipartite matching always, in this case, a price vector, so a vector P on items, is part of a Walrasian equilibrium. So remember, a Walrasian equilibrium is two things. It's prices and it's an allocation. Okay? So when I talk about a price vector, I talk about it being part of a Walrasian equilibrium. It's part of a Walrasian equilibrium if and only if P is part of an optimal dual solution. Okay? Again, remember, a dual solution consists of two things, a U and a P. Okay? So it makes sense to say part of a dual solution. All right? So in this sense, Walrasian equilibrium price vectors correspond precisely to optimal dual solutions, or rather their projection onto the item part, onto the price part. Okay? So again, this is sort of weirdly vacuous at the moment. This has some content. All right? So questions about that? And if you think about it, I mean, this is still pretty neat, though, in a sense. I mean, if you think about generalizing this, so, you know, the left-hand side, well, Walrasian equilibria, they seem to be about like nothing but prices. That's the whole point. They're about market clearing prices, right? The right-hand side actually isn't, okay, so first of all, whenever you see prices, you should think there's probably some duals in the background, okay? And we'll see that that is the case here. But actually, the right-hand side of one, that's not even talking about the dual linear program. That's talking about the primal integer program and its linear relaxation. So it's characterizing existence of prices in terms of exactness of a linear relaxation. Okay, so that's a neat connection. All right? And then the second part is something sort of one might expect to be true, but it's worth sort of just teasing out exactly what the formal statement is, and that's what it is. Okay. So let's prove this. And the proof is not hard. All right. So I'm going to prove something that is going to imply both 1 and 2. Okay? So I'm going to prove that a given pair, a price vector and an allocation, which in this context I can think of as a matching, is a Walrasian equilibrium if and only if the prices participate in an optimal dual solution and M is an optimal solution to the LP relaxation. Okay? So we have our integer program. We already know from the first welfare theorem that M is a max weight matching, so we know it's an optimal integer solution. And so, but here on the right-hand side, the assertion is that actually more generally, even if you allow fractional solutions, still M, this integer solution, is the best. Okay? So this implies 1 and 2. So why does it imply 1 and 2? So for example, so the second part is sort of, you can just read off from this. So the second part is really kind of almost a special case of what I have up there. For the first one, all right, so suppose a Walrasian equilibrium exists. Then on the right-hand side there, we have that M, this integer solution, is optimal amongst fractional. So that's a proof that opt IP equals opt LP. So conversely, suppose that the LP relaxation is exact. That means there's an optimal integer solution. There exists an optimal dual solution. And so you pair those together, and those together give you the Walrasian equilibrium on the left-hand side. Okay? So if that was too fast, I'll leave it for you to check offline. So we can get 1 and 2 in one swoop by just proving this. Okay? All right, so the harder part is this side. So suppose I give you a Walrasian equilibrium. Okay, so a price vector P and a matching M. All right? I guess that's too bad. So the dual's still here. Okay. Well, that's fine. So let X be the LP solution corresponding to M. Okay, so this is just notation. Okay, so M is a matching, X is just the characteristic vector of the matching, the zeros and ones corresponding to the edges in the matching M. Okay. Now, so that's fine. So this is talking about a dual solution and a primal solution. The primal solution that's relevant is X. So now there is some work we have to do. Okay, it's not hard, but we have to do it. So a dual solution, remember, so here's the dual. Duals have price, they have these P's and they have these U's. Okay, so to talk about something being an optimal dual, I need to tell you what the U's and what the P's are. Okay, and I've only been given the P's, so I have to tell you what the U's are. Okay. Looking ahead, I'm going to construct a dual solution and then we're going to verify that complementary slackness holds. And that'll give us the simultaneous optimality of both sides. Okay, so given that, we're going to do it in the obvious way. Okay, so again, we're given a Walrasian equilibrium. I have the P's, I have the prices, and it's really tempted to just sort of interpret those prices directly as a dual feasible solution. That doesn't make sense, so because I don't have the U's. All right, so how do I define U's? Okay, well, I want it to be feasible, and subject to being feasible, I want it to be as good as possible. Okay, where good here means minimizing everything. So I'm given the P's, right? The values are just fixed. Okay, so what does this say? So think about this for a fixed I. Okay, so remember we have to pick ui for each I. So this has to hold for all, so for a given ui, this has to hold for all j. Okay, or this has to hold for all j. Well, so this is just a bunch of lower bounds. The only relevant one is the biggest one. Okay, so basically, look, I want ui to be as small as possible. I make it as small as possible so that all of that holds, all those constraints hold. I.e., I set it equal to the maximum of the right-hand sides ranging over all items j. Okay, that's the obvious way to define the U's from the P's. So define ui to be the biggest of these lower bounds. Well, the only other rub, I guess, is that ui better be non-negative. Okay, so if all of those are negative, I better make it 0 instead. So this notation just means take the maximum with 0. Okay? Again, the point here is, i.e., as small as possible, subject to dual feasibility. Okay? All right. So now by construction, x and p comma u are feasible. What do I want to prove? I want to prove that they're both optimal. What's my tool given two feasible solutions for proving that they're both optimal? I just check that the complementary slackness conditions hold. Okay, so let's just see why that's true. Okay, so again, we're given a Walrasian equilibrium P comma M. I extended P to a dual feasible solution PU. I'm now claiming these three things are true. Why is that the case? Let's start with the first one. What does the first one say? It says whenever xij is bigger than 0. What does that mean? That means, remember, it's an integer matching. Okay, it's a 0, 1 x's. So it says whenever bidder I gets an item j, that's what this means, it has to be the case that this holds with equality, i.e. that this holds with equality, i.e. that the utility of the bidder is exactly its value minus the price that it's paying. Okay? Notice, how did we set the ui's? I mean, one way to think about how we set the ui's is we basically said, look at each good j, what would be my net utility for getting good j with my value at that price, and then set ui to be the highest of them, i.e. it's the maximum utility I can attain by picking my favorite good at price vector p. Or, if those are all negative, it's 0. Okay? So that means this holds. Okay? So it is the case in a Walrasian equilibrium, I'm getting my favorite good at those prices p. Okay? So that means the ui, which meets this with equality, or whenever xij is bigger than 0, it must be the case that ui meets this with equality by the Walrasian equilibrium condition. What does this say? This says, suppose the utility is strictly positive. Okay, so what does that mean given how we define the UIs? That means suppose there exists an item j, so that my value Vij is strictly more than the price. Okay? Well, in a Walrasian equilibrium, if I have positive net utility for some good, I have to be assigned to some item. I will not accept nothing. Okay? So if UI is strictly positive, it will be the case that if I'm bidder I, I'll get a good. Okay, so that works. And then this is familiar as just that usual second conditional Walrasian equilibrium. If a good is unsold, so look at the contrapositive. If this is 0, the good is unsold, then it must be the case that the price is 0. Okay? So note, CS1 through CS3 hold, and therefore X and P comma U are optimal. Okay? So X for the primal, even though it's an integer solution, PU for the dual. Okay? So that's one direction. That's starting from the left, going to the right. The other direction is even easier. Okay, so I'm not going to write it down again, but I'll just talk through it quickly. It's easier because I don't have to do this business with sort of making up UIs out of thin air. If you actually give me a P that's part of a dual solution, say part of P comma U, and you actually give me an integer solution to the LP relaxation, okay, an X, then by virtue of both of these being optimal, all three of these complementary slackness conditions hold. Remember, this was an if and only if. And the connection between Walrasian equilibria and these three connections is also an if and only if. Okay, so you just run it in reverse. Okay, you give me the optimal solutions, complementary slackness holds, that implies Walrasian equilibrium, done. Okay? So that's this argument. So if you like, a computational test for the existence of Walrasian equilibria is checking exactness of the LP relaxation. Okay? And as one would hope, there's an interpretation of Walrasian equilibria in terms of dual solutions, in this case optimal dual solutions, to a suitable linear programming relaxation. Okay, so that's the takeaway message for this theorem. Do you have any questions about that? All right. So like I said, this was sort of throwback, back to scenario number 3, but hopefully it's a little easier to keep track of what's going on in the bipartite matching setting. And the good news is that all of these conclusions just extend with literally 0 change to the proofs, to more general settings. So I do need to tell you exactly what the primal linear program is. But other than that, I'll just summarize the main statement. And if you want, I'll leave it for you to write the proofs down again, but it's literally just, word for word exactly the same. So, extension. To general valuations. Okay, and so for the current discussion, I'm not going to assume the gross substitutes condition. Okay, this is literally any valuation functions. What I'm going to say will be true. All right, so in the old integer program, we had an xij. Okay, all we kept track of was who got which good. Now people might want a bundle of goods. So instead of xij's, we have xis's, where s is a subset of goods. Okay? There are now many more decision variables than there were before. Okay, there used to be n times m, now there's n times 2 to the m. We're not going to worry about it yet. We'll worry about it later. Okay? Okay, so what's the analogous integer program? So again, we want to maximize welfare. So again, we sum over all of the bidders. We used to sum over the goods j that a bidder might conceivably get. Now we sum over the subsets, the bundles, that a bidder might conceivably get. We look at the value of that bidder I for that subset S times the indicator of whether it gets it. Before, we had a constraint that said everybody should get at most one good. That doesn't make sense because it's unit demand, but it does make sense to say everybody should get at most one bundle. So So for every bidder I, if we sum over the bundles it could conceivably get, you should only get one. It's still the case that every good should only be allocated once. So it used to be, right, so it's a little more complicated because now, like before, we have to sum over all the people who might be assigned good J, but also for a given bidder I, there's a number of ways you might get J. Okay, any bundle containing J counts. So in here we sum over all the bundles S so that item J is a member of S of I, XIS. Okay? So the assertion is that whatever the valuation functions, the integer solutions to this program correspond exactly to the allocations of goods to bidders. Okay, where everybody gets at most one bundle and every good is allocated at most once. And moreover, the objective function encodes the welfare. So if you could solve this integer program, you would maximize the welfare. Okay? And then again, the LP relaxation, you just replace the integrality constraints with non-negativity constraints. Again, putting on an upper bound of 1 was redundant in light of these. Okay? So any questions parsing that? So really just instead of the m individual goods J, we just have the 2 to the m possible bundles S. That's it. All right, so because the primals changed so little, the dual has also changed not very little. In particular, since the constraint structure is really the same. We have one constraint per bidder and one constraint per good. So in the dual, we're again just going to have the same set of n plus m dual variables, one for each of those n plus m constraints. So the dual now looks like the following. Exact same objective function as before. And so the covering constraint looks a little different. It used to be that a given edge, right, should be covered by the weights of its 2 endpoints. So now instead of an edge, instead of an item, we have a bundle. And each of the items in that bundle has a weight. But so we just have a bundle, and a bidder pair should be covered by the sum of the weights of the bidder, UI, and all of the PJs, all of the weights of the items in that bundle. Okay? So this is going to be for all I and S. It used to be for all I and J. This is going to be at least VI comma S. It used to be VI comma J. And now instead of just a single PJ, we take the total price of all of the items in the bundle J. And again, the economic interpretation is clearer if one writes this as the utility of bidder I should be at least, think of it as the maximum of the value for a bundle minus the price for that bundle. Okay? And for all I. And it's still the case that the U's and the P's should be non-negative. That hasn't changed. Okay? Any questions about that? Good? All right. So, rather than rewrite the theorem again, let me just leave it. So let me just say the following. In this setting, okay, with no assumptions at all about the valuations, with absolutely no rewording, although notice the only difference is the LP and the IP have changed. Okay, the LP and IP here now refer to this integer program and its linear relaxation. And as stated, this is still true with exactly the same proofs. Okay? Well, as an equilibria is also defined more generally now. rather than a bidder getting its favorite single good at the given prices, it's getting its favorite bundle at the current prices. The biggest thing I want you to notice is that it's no longer the case that one is vacuous. Okay? So remember, I showed you an example where there's no Walrasian equilibrium. Right? So when we had that single-minded bidder and the unit demand bidder, I mean, it's an exercise, but we talked through why there's no Walrasian equilibrium in that case. So at the current level of generality, which certainly can encode that example, this might be false. Okay? So in which case, this is also false. So for that two-bidder, two-good example, the linear relaxation is going to be strictly, it's going to have a strictly larger optimal solution than the integer program. Okay? We can just read that off of this. Okay? In that case, there will be no Walrasian equilibria, so of course this is not going to be the case. There are, of course, still optimal dual solutions. There are no Walrasian equilibria, so there's no correspondence between the two. Okay? All right, so this theorem holds totally generally. Okay? Walrasian equilibria existence is the same thing as exact LP relaxations. Cool. So, we actually know something about when Walrasian equilibria are guaranteed to exist. That was one of the main points, right, of the first lecture. Okay? So corollary, suppose every valuation function satisfies the gross substitutes condition. What did we learn in the first lecture today? We learned that Walrasian equilibria are guaranteed to exist. Right? So we had the Kelso-Crawford auction. That's what actually motivated us to state the gross substitutes condition. That terminates at an approximate Walrasian equilibria, taking the limit shows there exists a Walrasian equilibrium. Okay, so not in general, but with gross substitutes, we always have a Walrasian equilibrium. Which means then, with gross substitutes, the linear relaxation is always exact. Okay? And I do know other proofs of that fact, but I don't know an equally short proof. Okay? So the shortest way I know how to prove that the linear programming relaxation is exact for gross substitutes valuation is by proving that Walrasian equilibria exist and then invoking this theorem. Okay? So that's interesting. Okay, and so I hope you're getting some, again, because I only have sort of today to talk about substitutes valuations, I can kind of only show you the tip of the iceberg, but I hope you're starting to sort of see kind of how intertwined everything is, right? Because where did we start? We started with this, we started with this Kelso-Crawford auction, and we already knew it wasn't going to give us an incentive-compatible auction, right? We already knew it wasn't going to work even with downward-sloping valuations. We knew it wasn't going to work because it was hell-bent on finding a Walrasian equilibrium, which are not VCG payments, okay? Yet we went through that exercise anyways. Okay, well, what did we learn? Well, at least we learned that Walrasian equilibria exist. We don't know how to use those directly in an incentive-compatible mechanism, but we learned they exist. And now all of a sudden when we're talking about, okay, well, what about implementing VCG in polynomial time? Somehow those existence of Walrasian equilibria is the thin end of the wedge, as we'll see, in terms of an efficient procedure for computing welfare and therefore computing VCG payments. Okay? So again, somehow substitutes form the threshold at which a lot of properties go from true to false. Okay? Computational ones, like we're discussing now, and non-computational ones, like these. Okay? All right. So, neat. So now, let's actually talk about implementing VCG in polynomial time. Okay, so remember this. All right, so that's going to be important in our implementation. All right, so first, just a quick reminder. So VCG is a mechanism. It has to compute both the allocation and the payments. But again, remember the payments, the computations are the same as for the allocation. So VCG is just n+1 invocations of welfare maximization. Okay, so the question of whether or not we can implement the VCG mechanism in polynomial time is the same as whether, forgetting about incentives, just think about the algorithmic question, I just give you these valuations and ask you for the max welfare allocation. Okay, forget about anything else. Okay? up to a factor of n plus 1, the complexity is exactly the same. So reduces to welfare maximization given truthful bids. Okay? So for the rest of this lecture, we're talking about a purely algorithmic question. It's in service of getting this dominant strategy and setting compatible mechanism, but the VCG payments take care of that. Okay? We're just asking about welfare maximization. What's its complexity? Okay. So can we do this in poly-time? All right, so what do we mean? So we actually have, so if you think about it, we actually need to take a step back and talk about foundations a little bit. Okay, we're veering into we're about to start making statements that don't necessarily make sense or that are not well defined. When we say a polynomial-time algorithm, what do we mean? Polynomial in what? Polynomial in the input size. Okay, so if I talk about the problem of maximizing welfare with respect to a bunch of gross substitutes valuations, what's the input size? We have to think about this a little bit. There's a few answers. Okay, there's not some right answer to this, but there's an issue. Okay, and we need to make some modeling decisions. Okay? So let me tell you, so let's begin with sort of the most, sort of maybe most obvious and maybe the least useful answer. Okay? But also sort of the most conventional answer, which would be, well, I mean, you know, what did we say? We said valuation functions, it's just a, you know, it's a private value for every subset of bundles, right? So each person has these 2 to the m pieces of data, okay? And so the input size is just gonna be the list for each of the n bidders and each of the 2 to the m VISs, private parameters, it's just that list of numbers, okay? So we sort of envision all these VISs provided explicitly, in which case the input size would be roughly n times 2 to the m. Okay? Now, you know, if m is really small, maybe this is okay. Okay? Otherwise, if m is modest, this is really a huge input size. Okay, so this is exponential in the number of goods, which is maybe not that happy. We're not that happy about. Now that said, the algorithm I'm going to give you isn't at all practical, so maybe it doesn't make sense to kind of talk about practical instance sizes and so on. But the other reason this winds up to be not the most interesting approach for this problem is if this is your input size, it's actually pretty straightforward to solve this problem exactly in time polynomial in this input size, no matter what the valuations are, gross substitutes or not. Okay? So, in fact, it's easy enough, I'll leave it as an exercise. So very straightforward dynamic programming. You can actually solve this problem. Okay, so again, no assumptions, no gross substitutes. I just tell you that the valuations are monotone. And you want to find the best allocation of the goods to maximize the welfare. You can solve that in time polynomial in n and 2 to the m. Okay, straightforward dynamic programming. So let me say can solve in poly-time, where poly is polynomial in the input size, which in this case is this input size, by dynamic programming. So the real complaint we have here as modelers is that this way of modeling input size suppresses really interesting differences between different types of valuations. Okay? And this is a real thing in practice. So for example, in practice, when you want to solve these problems, combinatorial auctions, et cetera, they're much easier when there are substitutes, and they're much harder when there's complements. We'll talk about this more next week. But the point is, the actual real-world complexity of the problem depends on structure in the valuations. And if you model the input size this way, the theory is unable to tease apart those distinctions. Okay, so that's the main sense in which this is a failure, more than the fact that just 2 to the m is a frightening expression. Okay, good. So I'll tell you two other approaches. Both are reasonable. We're only going to talk about one of them today, but both are reasonable and lead to interesting and sometimes enlightening results. So sort of a good rule of thumb in this area would be that, and somehow we want a model where it's reasonable to ask for algorithms that run in time polynomial in n and m. Okay, in the number of items, not in the number of bundles, not in 2 to the n. Okay? So we have to ask ourselves, okay, so what notions of input size, right? So what do you learn in 161 or intro algorithms? You often learn, okay, you have to read the input. Okay? So we need to somehow have a notion of, a model of the input which is not exponential in n. Okay? To be able to have algorithms that run in time not exponential in n. So answer number 2 would say, okay, well, I guess I don't really mean totally abstract gross substitutes valuations. I mean, valuations would satisfy the gross substitutes condition and also have some, succinct representation. Okay? So think about like those k-unit demand valuations. Okay? So all I need to specify are n times m numbers, a vij for each bidder I and each item j, and then by definition your value is just sort of the top k of the vij's. Okay? If you get a bundle of goods, you just pick the best up to k goods. Right? So those are gross substitutes. Okay? Of course, it's not all gross substitutes, but it's a reasonable class of them, and you can specify them succinctly. And it makes sense to ask for algorithms that run in time polynomial in n and m. Okay, and that's reasonable. We're not going to do it today, but that's totally reasonable. So what are we going to do today? Well, so what we're going to do today is we're going to just think of each valuation. We're going to be agnostic as to how it's represented. We're not even going to try to model how VI is described. We're just going to model our input-output, behavior with these valuations. So we're going to think of each valuation as just a black box. Okay, that exists in the ether that answers queries. Okay, questions that we give it. All right, and if this seems kind of too, wishy-washy, let me point out that when we were talking about our ascending auctions and we were actually kind of envisioning interacting with bidders, we really were thinking of them as exactly this. Okay, we were thinking of sort of real human bidders as black boxes, where we say, these are the prices, what do you want? Okay, and we're not modeling their representation. We don't have a notion of their input size. We just expect an answer whenever we ask them a question. Okay, so it's actually not that unreasonable. Okay, okay, and so then the goal. Okay, so when you're trying to design an algorithm to say maximize welfare, what do you want? Okay, what's the analog of polynomial running time? Well, you just want to, so goal, so if you combine sort of the quote-unquote normal operations of your algorithm plus the number of queries that you ask the black boxes, the valuations, this should be poly in the number of bidders and the number of items. Okay? And so, because there's no explicit list of 2 to the m numbers, there's no obvious lower bound showing that this can't be done. Okay? And as we'll see, actually, this can be done in interesting situations. Okay. So one question that's natural to ask is, okay, what are these queries? All right. But again, if you think about the ascending auctions, we've seen the examples of these queries. Here are the prices, what do you want? All right. Now, in general, it's sort of negotiable when you do research on this problem, what the queries are. But obviously, when you're designing algorithms, proving upper bounds, the simpler and the more natural the query is, the better. Okay, the more plausible your algorithmic solution. So 2 of these people have focused on a lot. Okay, they're both very natural. So the first one we've kind of seen already in our ascending auctions is just a demand query, which is given prices Q. So basically you have this black box, you feed into it a vector of prices. and you're expecting it to give you back a set in its preferred bundle, okay, something that's demand set. So output a set of DIP. Okay, one of its utility maximizing bundles at the price is P. Okay, that's the
prices are just for individual items.
Exactly. In this case, it is. Yeah. Yep. Yep. Right. So basically, you feed it an M vector, and you get back a set. The other very natural query is just a value query, which is now you just ask a bidder seemingly simpler question, which is like, here's a set. What would you be willing to pay for it? Okay, give me just one bid. Here's the set I want to bid for. So given S, output VI of S. Okay. And it should be intuitive that, you know, sort of value queries seem simpler and easier than demand queries. Right? So like a value query is like me asking you about some product in Best Buy. You know, like that Xbox, how much are you willing to pay for that Xbox? A demand query is like, okay, there's price tags on all the items in Best Buy. Tell me which subset maximizes your utility at those prices. Okay? Which, you know, to be fair, like we do approximations of those problems all the time, but it seems like a harder problem. It's true even formally. You can show that you can simulate value queries with a sequence of suitable demand queries. Okay? So sometimes there's controversy about whether or not demand queries are okay, but frankly in an auction context, I think they're very fundamental. And then, you know, these should be even less controversial. Okay? Once you start doing anything else, it starts getting a little, you know, controversial if it's reasonable queries or not. Okay. So. All right. Is there any questions about that? Yeah.
It seems like demand query should be easier than value query because the easiest thing to do is a pairwise comparison, and you can get your demand query out of less than m squared pairwise comparisons. You have to do a pairwise.
That's not. Are you? Why do you say pairwise m's? These are on bundles, remember. So for a demand query, remember the candidate answers are all 2 to the m bundles.
But the when you work out your value query,
yeah,
as a business, you're really asking like how much money can I make out of this bundle?
Yeah.
Compared to like all the other like business strategies I could implement.
Yeah.
Whereas the pairwise demand.
Well, I mean, really in an absolute sense. Oh, you're saying including the opportunity cost.
Yeah.
Uh-huh. Yeah, okay, but I mean, still, I'd say here there's a sense, there's a sense in which this is really an optimization. It's almost like this is more just like a single estimate, and I'm not saying that's always easy, and it is an estimate, and you might not, and of course, you know, a real setting you won't literally know this, right? You might hire a team of consultants, and they'll give you pay them a lot of money, and they'll give you their best guess. So, point definitely taken that this is not necessarily easy in practice. You know, I'd say people solve this approximately, and people solve this even more approximately, would be my take, actually. Again, remember, this is optimization over a lot of different options.
But it's not optimization over things you can answer exactly, probably.
Sure. But somehow, I mean, I'd say here there's a notion, there's a aspect of search through a big space, which I don't think is here so much. You know, this is a non-formal statement I'm making, but yeah, and there is a mathematical statement about it, which basically says for any valuation, if you allow me the power to ask demand queries, I can answer any value query by invoking this a polynomial number of times at different prices, and the converse is false. Again, so now this is the math part, which you could argue with the model, but these are true statements. So there are valuations for which, if I give you the power to answer value queries, you need an exponential number of them to simulate a demand query. So there is a formal sense in which demand queries are only harder than value queries. Again, in practice, you can debate it. So. Okay, good. All right, so again, All right, so what's the high-level takeaway of this discussion? So the first high-level takeaway is just that, when you start dealing with these abstract valuation classes, like gross substitutes, you have to make some decisions about representation. And they're annoying, but you have to talk about it. The second thing is just that for today, this is our model. Okay? Valuations are black boxes. We can ask them a demand query, we can ask them a value query. We count those as just one step of our algorithm. Everything else is one step. And we want to be polynomial in the number of bidders and the number of items. Okay, that's the goal. And the main result that I want to sketch a proof of in the time remaining is we can achieve that goal for welfare maximization with gross substitutes valuations. Okay? So theorem. With a black box, gross substitutes valuations. Can compute the welfare maximizing allocation. And hence, running it n+1 times, we can compute the VCG outcome in poly steps. Poly of nm steps and queries. Okay. And so warning, the algorithms I'm going to give you is about as impractical as you could imagine. Okay, so this is a purely in principle result. But again, these gross substitutes, it's very abstract in general. Okay, so to have such a general result, we have to expect pretty heavy machinery would be required. Moreover, we'll see next week that if you generalize gross substitutes just a little bit, you cannot do this. Okay, so there are lower bounds saying you cannot get exact welfare maximization in polynomial time. All right. So we're again going to use linear programming, but we're going to need a tool beyond what we've discussed already. So who among you have heard of the ellipsoid algorithm? Raise your hand. Okay, and who has not heard of the ellipsoid algorithm? 50-50. Okay, that's about what I expected. So, good. So let me tell you a little bit about it. Basically, the ellipsoid algorithm is total magic. That's the one sentence explanation, okay? So all right, so there's certain kind of linear programs we can solve well in theory and in practice, and those are the ones that are explicitly described. Okay, so if you have a reasonable number of variables and you write down an explicit list of a reasonable number of constraints and it's a linear program, we can just, we can solve them in practice. We have pretty good theoretical bounds and so on. It turns out, at least in principle, we can solve linear programs which are not explicitly described in this way. Okay, and we can't use an arbitrary linear programming algorithm to do that. We have to use a special one called the ellipsoid algorithm. So let me elaborate. And I should say, independent of this class, this is a tool worth knowing. Okay, if you're ever interested in, proving in principle tractability results, polynomial-time tractability results, the ellipsoid algorithm can do things that pretty much nothing else that we know of can. Okay, and it's not a recent algorithm. So this was developed by Kachian in '79. Okay, but to this day, it feels very magical. All right, so let me tell you the kinds of linear programs that the ellipsoid algorithm can solve in polynomial time. So consider a linear program with, so the number of variables needs to be reasonable. Okay? So let's say capital N dimensions or decision variables. Okay? And so just looking ahead a little bit, remember that in our primal linear program that we wrote down for welfare maximization, we had a decision variable for each bidder in each subset of goods. So this is exponential in M. Okay, so it's not actually clear why this ellipsoid algorithm is yet going to be useful. Okay, because that linear program already had too many variables. But bear with me. So 2, any number of constraints. So this is the magical part. So concretely, think of the number of constraints as being exponential in the number of variables n. Okay? Now what's the catch? So the catch is it's important that this large set of constraints, it's important that you can efficiently search for one that is violated. Okay, so this is called a separation oracle, or a cutting plane in certain other contexts. So a polytime, so here polynomial means polynomial in n, and the maximum number of bits used to describe any number. So a polytime separation oracle. So what is this? So this is an algorithm that takes as input an alleged feasible solution to this linear program. Okay? Maybe it's feasible, maybe it's not. It's supposed to be feasible. Someone claims it's feasible. And the separation oracle is a verifier. Okay? It's supposed to be fast, but it's supposed to be able to figure out whether or not this purported feasible solution really is feasible. Okay? Now, if there's only a polynomial number of constraints, this is really easy, right? If you give me the alleged solution and there's a small number of constraints, I'll just check each one, no problem. The problem is when there's an exponential number of constraints, and you give me an alleged solution and I can't check them one by one, okay? But if it's the case that I can, in polynomial time, verify them all, then it's a separation oracle. Actually, I need a little bit more. If it's feasible, then you can just tell me. I mean, you have to be correct, but you can just tell me that's feasible. Now, if it's infeasible, it's not enough to just tell me, okay? I need a proof that it's infeasible. By a proof, I mean an inequality which is violated by the alleged feasible solution, okay? So that's a separation oracle for a given linear program. Okay? So if I assign a number to each of the decision variables, I can invoke this algorithm that says good job, feasible, or it says infeasible, and here's why. Okay? And it should run in polynomial time. Linear programs that satisfy properties 1, 2, and 3 can be solved in polynomial time. Not by any old linear programming algorithm. Almost all linear programming algorithms need an explicitly described linear program, but it can be solved in polynomial time using the ellipsoid algorithm. Okay? And when I say polynomial time, I mean polynomial in n and the max number of bits needed to describe any number. Okay? Importantly, independent of the number of constraints. That's the whole point. Okay? So that's just a fact. All right? I'm not going to prove it. If you're curious, I wouldn't be too frightened of it. Like in a 75-minute lecture, I could give you the gist of this algorithm. Okay? It's not kind of algebraic geometry or something. Okay? It's messy, but the conceptual ideas are actually nice and understandable. All right? But for now, most practicing researchers just accept this on faith, that this thing exists, and then uses it as a tool. And you are welcome to do the same. Okay? And it's good to know. You should know that this is possible. I should also say that thinking in this way isn't necessarily have nothing to do with practice. I mean, these separation oracles are used to this exact same problem arises in so-called cutting plane algorithms, which can be very practical methods of solving integer programs. Okay, but for now, this is what we're going to use. All right. So any questions about that? I'll try to find some good lecture notes on the web and post them on the course site about the algorithm if you want to learn a little bit more about it. Okay. Then we're just going to accept that the ellipsoid algorithm exists. And now I'm going to show you a proof sketch of this theorem. Okay? Why welfare maximization is possible with gross substitutes. And again, remember, this is not going to be possible even a little bit beyond gross substitutes for so-called even submodular valuations. We'll talk about that next week. All right. So proof of theorem. All right, so what might we apply the ellipsoid algorithm to? So the ellipsoid algorithm, powerful though it may be, the running time does scale with a number of variables. And the linear program that we care about the primal linear program, which remember we know is exact. Maybe I'll leave that over here. Right, so holds for GS valuations. So again, we're trying to prove something specific to gross substitutes valuations, right? So we're actually going to use the gross substitutes condition in two different ways. Well, no, really, one main way. So the main thing gross substitutes is buying us is it guarantees that we don't actually have to solve an integer program, which would be scary. We only have to solve a linear program, which is less scary. Unfortunately, the linear program still has 2 to the m decision variables. So it's not amenable to the ellipsoid method. However, so if you remember that linear program, I'll write down the dual again. I won't write down the primal again. But in the primal, we only had one constraint for each bidder, saying I got at most one bundle. And we only had one constraint for each good, saying it's only allocated once. So the number of variables may have been big, but the number of constraints was small, just n plus m. So not coincidentally, in the dual, we had a small number of variables. Okay, the UIs and the PJs. Yeah, we had a ton of constraints, but then we're in the wheelhouse of the ellipsoid algorithm. Okay? So the idea is, okay, first of all, gross substitute says we only need to solve a linear program. Second of all, the dual has few variables. Let's try to nail it with the ellipsoid algorithm. Okay. So step 1. So try to solve dual LP, or apply ellipsoid. And it's actually going to be important we remember what this is. So minimize the sum of the UIs plus the sum of the PJs subject to UI plus sum. So basically every valuation should be covered. And again, better to think of this as UI at least max S VI S minus sum J and S PJ. And non-negativity constraints. So apply ellipsoid to the dual LP. So the big question then is, do we have a separation oracle for this dual LP? If we have a separation oracle that runs in polynomial time, then the ellipsoid algorithm will solve it in polynomial time. Right? That's what the ellipsoid algorithm does. It reduces solving the LP to just designing the separation oracle. So let's think about the separation oracle. So given an allegedly feasible dual solution U comma P, well, the non-negativity constraints, there's only a small number of them. So we just directly check that we only are given non-negative numbers. Let's look at these constraints. Okay, so remember the V's are just part of the data, and we were just given these allegedly feasible U's and P's. Okay? So this is for all I. Okay? So there's only I bidders, no big deal. We can enumerate over the n choices of I. The scary thing is that there's these 2 to the m possible S's, okay? But because these are all just lower bounds, okay, because each S just gives us a lower bound on UI, we just have to check that UI is as big as all of the lower bounds, i.e. as big as the biggest of the lower bounds. And this looks pretty familiar, right? This is actually just a demand query, right? So the maximum over S of this is just saying, look, amongst all the bundles you could buy at the prices P, which one maximizes your net utility, right? That's a demand query. So by assumption that the valuation, this may seem like cheating, but you know, if you believe the demand, if you're thinking about a world where demand queries can be answered quickly, then with one demand query, you can in one fell swoop figure out which set achieves this maximum. Okay? That's what a demand query does. Now, given this set S, with a value query, you can just figure out what this number is. You have those numbers. You can just compute what this largest possible right-hand side is. And you just compare it to U sub I. Okay? So demand query lets you evaluate the right-hand side. You just compare this inequality, there's n such inequalities, and you're done. Yep.
Like, given that the bidder to have to do demand query has to search to the n possible space to the n, like, isn't it just offsetting the computational cost to the bidder as opposed to the mechanism?
Well, it's really, so it's a good comment. And in effect, yes, okay? It is sort of pushing, it's sort of delegating the computation to the bidder. So a couple of things I'd say. So first of all, you could think about, so there's a relationship between these two different, the second approach and the third approach, okay? So you could ask the question, is a query reasonable or not? And you could ask, how would you make the case that a given proposed query was a sensible thing to include in the model or not? And you could use both mathematical and non-mathematical arguments to do that. The mathematical argument would say, well, consider all the concrete representations we actually might use. Unit demand bidders, downward sloping valuations, k-unit demand. And you might argue, well, in any of those concrete implementations, representations, we can implement these queries in polynomial time. Okay? So think, for example, about k-unit demand. Well, let's start with unit demand. Okay, so demand query is very easy for a unit demand bidder to implement. Right, it just goes through the different items, and it just does brute force search basically. If it's k-unit demand, so that's when you're happy to have up to k goods, then you would just sort things by Vij minus Pj and take the top k. Now implicitly you are searching a space of size 2 to the m, right? There really are kind of m different bundles you might pick, but somehow for that valuation the only relevant ones are the prefixes, so the effective search space is much smaller. So this would be how mathematically you might argue that a given query is reasonable by actually giving explicit polynomial time implementations of it for representations you care about. Now, full disclosure, there do exist not somewhat reasonable concrete representations where it's NP hard to evaluate a demand query. So the mathematical evidence I think is sort of a little bit mixed on demand queries. Often they're efficiently implementable, sometimes they're not. So for demand queries, a big part of the argument is just non-mathematical. It just says, this is just kind of, in an auction context, we're thinking that bidders can answer questions like this. And we already asked them to do this in complex auctions as it is. But mathematically the comment's a good one. Okay, we really are, but I mean from a modeling perspective, what's helpful is it sort of, isolates the relevant exponential search, okay? Because at least it's just sort of one bidder making a kind of local exponential search, right? So something which is intuitively much harder would be, okay, if I have n bidders and I have m goods to split amongst them, right? There's an exponential number of allocations, but sort of now the number of bidders matters as well, right? So at least this kind of reduces just saying locally each bidder should do its own exponential search within its preference space, which arguably is still some kind of reduction in the computation required. But yeah, it's a good comment. It's a really good comment. Okay, right. So the upshot is, assuming that demand queries can be implemented efficiently, gives us a separation oracle that can be implemented efficiently, and then feeding that into the ellipsoid algorithm, that allows us to solve the dual linear program in polynomial time, counting demand queries as one step. Okay. So use demand queries to check the rest. Okay. All right. So that's what we just did. Okay, we looked at the dual linear program, and we used the assumption that we can solve demand queries to solve it optimally. So step 2. So by strong duality, now remember, we don't really care about a dual solution per se. Okay, we passed to the dual because that's what had small dimension. So now we learn that the optimal dual solution has objective function value 1,322. Okay, so what? Well, we do have strong duality going for us. So we know that the value, okay, so now at this point in the algorithm, we know what is the maximum attainable welfare. We don't know how to attain it, but we know it's 1,322, okay, because we solved the dual optimally. So by strong duality, know the value of opt of the primal linear program, which by gross substitutes is the optimal solution to the integer program, i.e. the welfare maximizing allocation. Okay? And now step 3, so now, I don't know if you've seen this before, but in general, for so-called self-reducible problems, which is most of the problems one thinks about, given an oracle telling you the value of an optimal solution, by invoking it over and over again, you can actually reconstruct an optimal solution. Okay? So so like SAT would be one example. Suppose I gave you an oracle that just told you whether or not a formula was satisfiable or not. Invoking that over and over again, you could reconstruct a satisfying assignment of a satisfiable formula. And if that's something you've never thought about, that's a good thing to think about. So I'll put this on the exercise set. Okay? So step 3, so again, what's the context? We know the welfare we're shooting for. We know the best we can do is exactly 1,322. The question is just who gets which good. Okay? And again, like for example, what you could do is you could take good number 1, you could try giving it to bidder number 1, and then you could solve the residual problem. Okay? And look at the welfare of the residual problem. Again, if you don't like the answer, you could go back, you could backtrack and try giving good 1 to somebody else instead, and so on. Okay? So use this oracle sort of over and over again to guide your search, to sort of guess what the optimal solution has to look like. Okay? Okay, so again, I should emphasize this step is where we're using the gross substitutes property. Okay? And so we're using it with gross substitutes. The Walrasian equilibrium exists. We prove that using Kelso-Crawford, and then we argue that that implies that this is also the optimal integer solution. So use self-reducibility. To reconstruct a welfare maximizing allocation. All right. So let me just sort of tell you where we're going. So this pretty much completes, there's lots more one could say, lots more cool stuff, but there's just too many other topics to cover. So this is pretty much where we're going to wrap up with sort of non-NP hard, the tractable special cases of allocating resources to maximize welfare. It's also going to be pretty much the last, well, that's not quite true, but because the problems get harder, we'll actually look at more modest goals. So it's even going to be interesting to look at direct revelation DSIC implementations. For the next couple of weeks, we won't talk about ascending auctions quite so much. I guess I didn't close the loop and tell you about ascending auctions for gross substitutes. The picture is actually a little murky, so I don't want to talk about it right now, but I'll open with a few comments next week. And then we'll start looking at 2 more valuation classes, submodular valuation functions, which in some sense are just a step beyond gross substitutes, and we'll see a lot of the things that get harder. I also want to talk a little bit about complements. So when there are synergies between goods, those are also relevant in practice. So I'll talk about a notion of restricted complements, where there's some pretty juicy open questions about dominant strategy implementations. So I'll leave it for today and see you next week.